He's from Rob Hood, who's from the Wyss Institute. Did I pronounce that right? I don't know how that worked out. But Rob has been at Harvard University since 2006, and in that short time, he's had quite an impressive start, perhaps amassing more young investigator awards in the number of years than anyone I ever heard of, which includes the National Science Foundations, ONRs, DARPAs, and the Air Force Research Office.
AFOSR, yeah, Air Force Office of Scientific Research.
Better than me, because they're your sponsors. He's also won the Presidential Award, which was given to him by President Obama this year. And these awards speak not only to the depth and quality of his research, but also the breadth of work that he's doing. So today, we're probably only going to see one slither of the talk, but please don't hesitate to push him around and ask him some good questions. I think he's up for it. So thank you.
Thanks, Howie. Appreciate the invitation to come and speak with you. I'm going to be talking, as Howie mentioned, mostly on topics associated with our work in flapping wing micro-air vehicles. We have started some work a number of years ago. Well, this started from my grad work in Ron Fearing's lab at Berkeley, carried over to Harvard, and a few years ago we had a demonstration where we were able to assemble components of a micro-robotic flapping wing device and show that we could create a lift to weight greater than 1. And that was a cute demo, but in reality what happened was it launched us on a number of different research directions. And what I'll do is I'll point out basically everything else that I'm going to talk about today is motivated by the following facts. This is sliding up a rail, so it's not controlled. It's, you can notice the wires here, so it has no power. And there's other more subtle things like how do we build them, how do we understand aerodynamics for these things, how do we optimize design, and that's it. So those are the different topics I'm going to talk about. One of the things I'd like to clarify first, though, is that we are roboticists, and we're making, for example, robotic insects. Why do we want to do this? Not just to make cool robots. In fact, we think that there's a number of different things that will come out of the development of flapping wing micro-robots, ambulatory micro-robots, in things like open scientific questions. So using the devices for questions in, for example, low Reynolds number flapping wing flight, pushing different control techniques for computation-limited systems, system-level design, as well as doing some technology pushes, like how do we build on these interesting scales? How do we think about milligram scale power electronics, novel sensors and actuators, et cetera. So these are the themes of my group. What I'm going to talk about are a little bit of an overview of insect flight to get everybody on the same page. How do we build these things? How do we, if we can build them, then how do we start thinking about design for these systems? And in particular, they're extremely complex, and I'll get into that. How can we use, as I mentioned in the previous slide, how can we use some of these devices to study structure-function relationships for flapping wing devices, both natural and artificial? How can we think about control for these systems? How do we power them? And then in the end, if I have time, I'll talk about a new program which we have called RoboBees, which is a large NSF program developing a colony of autonomous robotic bees, as well as some of our other work in soft robotics, programmable matter, ambulatory robots, and soft orthotic devices. First, okay, to get everybody set up on the same page. One, how do insects fly? And this is remarkably different, of course, than what we would consider for classical fixed-wing aircraft, of course. And in fact, this was discovered, a lot of these insights were discovered by one of our colleagues back at Berkeley, who was back at Berkeley, is Michael Dickinson. He did some very phenomenal work in creating dynamically scaled models of what actual insect wings are doing. What I mean is he observed actual insects, Drosophila in this case, in free flight, looked at what the wings were actually doing, created dynamically scaled models of these systems, immersed them in things like mineral oil to match Reynolds numbers, and then flapped those same trajectories in the wings and measured things like forces and moments acting on the wings, and they were able to identify some key components of what they collectively called unsteady aerodynamics. And what these terms are, again, to put us all on the same page, assume that we have an insect with two wings, so flies, something which are nominally flat wing trajectories, nominally symmetric, periodic, with 2 degrees of freedom. So there's 3 potential degrees of freedom in the 3 Euler angles, but I'm only really going to be talking about flapping the wing in a horizontal stroke plane and simultaneous rotation, pronation and supination about a leading edge, about a axis parallel to the leading edge. So you have these sort of motions. And you think about this as sort of treading water in air. And what they were able to do is identify, quantify and qualified, different flow phenomenon associated with these sort of motions at the Reynolds numbers that we're talking about. And these sorts of things are as follows. Well, insects are able to, and flies in particular, are able to maintain very high angles of attack throughout the majority of the wing stroke. If you were to take an aircraft wing at higher Reynolds numbers and put it through even modest angles of attack, of course the leading edge vortex is going to grow, it's going to become unstable, it's going to shed. That's going to cause a catastrophic loss of lift to drag, and that's called stall. Insects have the capability, flies have the capability to delay stall through mechanisms of, well, a number of different mechanisms which basically stabilize that leading edge vortex. I'm not going to get into those details. That allows a large angle of attack throughout the wing stroke. That's one component. Rotational lift. At the end of each stroke, you have this quick flip, which is sort of gives you a rotational component to your force in a way down on like a curveball. And then finally, there's this pocket of fluid that I'm carrying behind my wing. As I reverse my stroke, I'm going to hit that fluid to get an instantaneous increase in the effective velocity that I'm seeing. So all of these sum up and say, okay, well, there's these unsteady aerodynamic things that are happening. And they gave us an understanding of what's going on. They basically said, well, you do a number of these different things. You move your wings in this particular way at these sort of velocities and these sort of kinematics, and you should be able to do things like get off the ground, which is what we showed. So that's great. Okay, so now we're all on the same page. Now we get into topics of, okay, with that sort of understanding, then how do we start thinking about building these structures? Okay, so first thing I'm going to do is get into a little bit about what is the basics of the structures which I'm going to talk about. Again, we're talking about a structure which it can flap its wings, 2 degrees of freedom each. It looks loosely like this with some actuator, which is, I'll get into the details of all these components. Some actuator which has a roughly linear output, transmission system which is mapping the linear motion of the actuator into rotations at the base of the wing hinge, creating some of these motions. And if we zoom in on this, you can see some of the degrees of freedom of the structure itself. And if we zoom in a little bit closer, you can see there's a passive element within the base of the wing hinge, which is allowing some of these modes to actually occur passively. So we take advantage of some passive dynamics, and without getting into too much details there, we think that that's a very effective and efficient thing to do for power distribution amongst something that's basically putting the vast majority of its power into overcoming mg. Okay, so that's the basics. Piezoelectric actuators, I'll come back to this, but we have the ability to manufacture piezoelectric actuators which are appropriate for these scales and these operating frequencies, probably not appropriate for much larger scale systems, but for these they work nominally fairly well. I'll get into that later on. This is what the flapping motion might look like if we're looking sort of end on. And if we want to get here's a real life video. This is actually taken at 10,000 frames per second. The wingspan is about 15 millimeters. I'll come back to this, but you can sort of see the sort of features we imprint on the wing, because we're going to start to try to look at how is the wing moving and deforming during flapping, and how can we understand those different deformation modes in terms of the aerodynamic structures of the wing.
Question?
Yeah.
What's the scale, size scale?
The wing itself is about 15 millimeters, so this is about 15 millimeters. So, okay, that said, how do we start to build these structures? I usually put it in a motivation slide, but I figured I didn't need to in the sense that we're not going to be building these structures with macro-scale machining techniques, and that should be fairly obvious in terms of resolution limitations, as well as some of the things you're going to classically do at larger scale structures using bearing joints or rigid links. Reason is basically physics of scaling is going to say that as you get smaller, your surface area to volume ratio is going to increase, and things which are relying on surface contacts are going to become extremely inefficient or just simply freeze up. So instead, we very, very intuitively simple, we rely on compliant mechanisms, so flexion mechanisms. And we have distributed compliance about quasi-two-dimensional structures. I'll get into very briefly how we make these things, but the basic structure is quite simple. You have 2 rigid face sheets of some rigid material. In this case, they're typically composite materials, ultra-high modulus composite materials. And they sandwich a thin film polymer. Where there's gaps in the face sheets, there's a flexible joint. Where there's not, there's a rigid component. And the nice thing about this is you can do this in arbitrary two-dimensional patterns. It's provable that given proper design over your two-dimensional systems, you can create three-dimensional systems with any number of arbitrary degrees of freedom from 0 to very large, okay? And so what you're left with is, after this process of cutting and micromachining and stacking and laminating, you're left with these different two-dimensional, quasi-two-dimensional components. We've recently had some nice success in being able to basically batch fabricate these things. The goal, I should say, is not only to be able to do these things, like I said, produce transmission systems with particular qualities, but to be able to do this extremely cheap, extremely fast. I'm very impatient. And furthermore, as you'll sort of gather, our group is extremely empirical. One of the reasons is because we know so little about the things that we're studying that we need to build them and learn by doing, learn by failure. And so what we really want is a process cycle which goes from concept design, fabrication, assembly, testing, we always test a failure, and analysis all within the scope of a week. And we can do that now with features on the order of 50 microns and yields which are nearly 100% and alignment which is nearly perfect. So without getting into too much details of that, turns out we can use those sort of techniques to make things like rigid airframes and the thing that you saw on the previous slide are these unfolded versions of spherical 5-bars. I'm not going to get into the details, but you'll notice that they have features which when you assemble these things, you basically fold them into single configurations which form the three-dimensional structure that you want. In this case, on the upper right is a spherical 5-bar transmission mechanism, which is another variance on flapping the wing in 2 degrees of freedom. Things like full-on wing drivers, I'll come back to these structures. But nonetheless, we can build these structures. We can build actuators, various components. We can start to build airfoils, which I'll come back to and give you some of those details. Turns out this is very important. We want to basically take notions of the gross morphology of natural wings, for example, and start to understand what's actually going on by building the structures and actually testing them. So how do we build them? I'll come back to that. Okay, so that, very briefly, is we can make things. Now, next question is, well, how do we start to actuate these things? And this is actually the subject of some of my graduate work, where we said, well, in reality, what we want is an oscillating input into this resonant system. And so we could use things like, hypothetically, we'd use things like electromagnetic motors if it weren't for a number of different things. I mean, well, again, the physics of scaling is going to say that any bearing joints are going to be very costly in terms of efficiency, but there's more subtle things like, for example, current density considerations for how much power you can start to dump in a coil of wires, coil as you start to decrease its characteristic dimensions. But also subtly is, well, we really want an oscillatory input. So if we wanted to have a rotary input converted to an oscillatory input, we have to have intermediate mechanisms. And so what we did was we looked at a number of induced strain materials, and by that I mean taking some simple stimulus and converting it to some simple length change. And so things like piezoelectric materials, be they bulk or single crystal, phase transition materials, electroactive polymers, be they ionic or dielectric, and lo and behold, the things that we could start to do is think about very simple models of this harmonically oscillating system and transferring what is the mechanical work from the actuator through a transmission system like I described to the wings. Do this for a couple of design breakpoints for various classes of vehicles. Use very simple geometric models for what these actuators might look like as a function of these different materials, and then start to say, well, as a function of force and displacement or frequency and work or mass and power density, what is going to be the appropriate actuation technology appropriate for these? And lo and behold, we settled upon these quite simple structures, which are these clamp-free bending bimorph cantilever structures, which are, you can think about these as just two parallel piezoelectric plates. You apply a field to the upper plate. Let's say it wants to contract. It can't because it's constrained by its boundary conditions, and so it bends. And you do this on the opposite plate, and it bends the other direction. They're very simple. They're very easy to make. We can make them across a variety of scales. The nice thing is that they have a couple of nice things. One of the nice things is that they have a very high bandwidth, which is good for the frequencies of operation that we're talking about, on the orders of 100 to hundreds of hertz. They have, like I said, they're relatively easy to make, but they have some negative sides. They're quite brittle. They're basically strain limited in terms of their operation. The point of the clamp-free cantilever configuration is actually to get an effective amplification, a first amplification stage of these strain limited, like 0.1% strains into 5% effective strain, meaning that what's the largest distal displacement normalized to the largest characteristic length of the actuator. But the other nice thing is since they're have a relatively high bandwidth, the power density output of these structures, which is really what we should care about, is approximately a linear function of the operating frequency. And so what we can do is think about these systems as oscillatory inputs into resonant structures. As the characteristic length of the whole fly, for example, starts to get smaller, your resonant frequency is going to monotonically increase. And so as that resonant frequency increases, then these things get better. okay? And we've shown that even though their bulk-free, strain-limited properties are on the order of a couple joules per kilogram of work output, not very good, you're operating at 1 to 200 hertz, so these things actually get pretty good. They get into the few hundred watts per kilogram range, which is greater than insect flight muscle, and on the order of pretty decent electromagnetic motors independent of scale. Okay, now, switch gears a little bit here and say, okay, now we can build things and we can actuate them, that's great. Now, how do we start to think about this? The overall goal of basically the flight apparatus, if you will, is to provide us with a platform which is going to stay aloft for as long as possible. Very basic. So it's not just sufficient to slap together actuators and electronics and your transmissions and whatever and expect to have a nicely operating vehicle. And so seems fairly obvious, but what it really means is that we need to do some pretty simple but nonetheless powerful system level modeling and analysis, and look at the point of the next few slides is just to say, I've got these different components. They all have their limitations. They all could use some more effort into improving them, and I'll get into that. What is going to be the biggest bang for the buck in terms of how much, if let's say, for example, if we can increase battery energy density, storage capacity, then how is that going to affect the overall flight time, which is our ultimate metric, et cetera. And so we can start to think about these systems as having two classes of components, lift producers and lift consumers. And what I mean by this is, if we think about lift consumers, then each of these components, some payloads or the energy source, actuator, whatever, they're going to have associated masses, okay? And you can think about mass as equivalent to required energy if we're talking about the energy required to just keep that mass in the air. If we talk about lift producers, then we can think about the energy source and all of the different transmission mechanisms, the energy source, the actuator is a transducer, a mechanical transmission, wings, et cetera, having certain different power outputs, efficiencies, and energy densities. And we can then take these and very simply just say, well, the flight time is just going to be some weighting of all of these different terms in terms of the total energy on board multiplied by all these efficiencies and normalized to masses and powers, et cetera. And P arrow being the power required to overcome mg. Then what we can say is, from very simple first principle models of what's going on here in terms of how do we model the actuator, how do we model the transmission, how can we do some simple models of the transfer of work from the transmission to the air, how can we start to think about how do we navigate in this rather complex design space is one. And then we can think about, well, how if we combine all of these different aspects from models of each of the individual components and plug them into our equation for flight time, how does that look like? And how do our choices for some of these geometric parameters compare to natural insects? So that's what the next few slides are going to show is we can use some trends, and there's some well-established trends in the insect literature to say, well, how do things like, for the mass of an insect and how is its flapping frequency scale, and things like, mass and wing area and mass and percentage of flight muscle mass, et cetera. And, all of our designs are roughly consistent with what you see across a wide order of different insect species. But what you will notice is that given these contours that you see here, given the state of the art for all of the different components which add up to the flight time estimates that I showed in one of the previous slides, we're estimating a very low flight time in the order of tens of seconds, which is not terribly good, right? So what this allows us to do is say, okay, well, let's think about this now and say, what are our assumptions on where these numbers are coming from? Current existing battery energy densities. Okay, we know that from commercial trends. Actuator energy densities, well, we know that from our own experiments. Power electronics efficiency, we know that from our own experiments. Payloads, these sort of things. Okay, that's state of the art. What would happen though if we start to improve upon each one of these things? And what I'm going to do is just say there's some improvement factor from state of the art to whatever that improvement would be over enhanced flight time by effectively improving upon all of these different metrics. And so we can start to look at how sensitive is our flight time and how this improvement factor 2 changes in these different technologies. So things like payload, well, we also have to put some upper limits, upper bounds on all of these things. Like, well, payload, we have to have some payload for computation and for sensing, et cetera. So we can't reduce that by too much. In terms of the actuator energy density, well, we can increase that a little bit, but we're limited by the strain limited bulk energy density of these piezoelectric materials, power electronics efficiencies, which I'll talk about, aerodynamics efficiencies, and the energy densities associated with the onboard power supply. So I'm not going to talk about this, but we have collaborations through the RoboBees project to do micro solid oxide fuel cells, which are appropriate for vehicles of this scale, and we're using that as sort of the best case scenario for what can happen in terms of onboard energy storage. And so we can start to look at, just going back to the previous slide that we had, very short flight time, limited mass range, and if we start to take some conservative estimates on what we can improve in terms of the different qualities of our system. Aerodynamic efficiency, let's say we get 20% better. Energy density of the energy source, 50% better. Then we can start to improve flight times by an order of magnitude or more. And the point of these last few slides is just to say, how do we direct our research? So if one of these things isn't going to affect us, is going to have a minimal effect on overall flight time, then we're not going to care too much about it. And in fact, what we are going to do then is say, well, one of the big wins that we think is going to be aerodynamics, okay? And so we're going to put a lot of effort into aerodynamic testing for the purposes of understanding things like the structure-function relationship for natural insects, flapping wing devices, but also for designing better vehicles, which would have different higher quality improvements. Okay. So to give a little bit of a higher order overview of some of our aerodynamics testing, a lot of people can start to think about this. If you look at an insect's airfoil, it's quite a complicated structure. You start to think about, all of the different design parameters it might have. These vanes of different sizes, three-dimensional surface topologies, surface texturing, aspect ratios, area distribution, all of these different things, right? It's very difficult to start to say, well, what is the function of this particular vane, or what is the function of this this surface property? And some people can start to think about, well, you do dynamically scaled models to start to explore some of these aerodynamic properties, and people have done this, as I mentioned previously, in some of our biologist colleagues, and it's led to some remarkable breakthroughs in some of these understandings. But certain things don't scale, fundamentally scaled in different ways. If you dynamically scale models to match Reynolds numbers, you're matching the ratio of viscous to inertial forces, but you're not doing anything with aeroelasticity. So compliance scales in a fundamentally different way. You start to think about doing these things with biological studies, but then you're limited, of course, to what you can get biology to do, which is not a lot and very frustrating. And we're not computational fluid dynamicists, and furthermore, the things that I'm about to tell you we can do in time scales which are much faster than the best supercomputers can solve these partial differential equations which would define the flow around these structures. So, anyways, we're not aerodynamicists, we're roboticists, and as such, the goal is to use our tools in terms of fabrication, actuation that I just showed you, the ability to manufacture airfoils and flap them around, to do some studies on how do we understand the role of these different morphological features in natural insect wings, how can we start to apply this to the design of better micro air vehicles, and it's highly empirical. So the first question you need to ask yourself is, well, how can we manufacture these airfoils? And so we've done this a couple of ways. The first way, which I'm not going to talk to you very much about, is basically to merge some of our the fabrication techniques that I was describing earlier with some soft lithography techniques to make micromolded channels that you then use to sculpt carbon fiber venation patterns. And lo and behold, if you do this and copy the gross morphological features, at least in 2 dimensions, of some of these natural insect wings, and it matches up with static stiffness properties, and it looks like it matches nicely to the particular species. But what we really want to do is say, well, let's that was very difficult to make those wings. Okay, so that's the thing I'm not telling you. So we'd like to make wings which we can sort of rapidly prototype through, as with the rest of our philosophy. But B is it doesn't capture the richest set of morphological features that we might want to look at. And if we start looking at this, is in this case a micro CT scan of a hoverfly wing, and we start looking at, well, look from base to tip here, and it's got these corrugation patterns and these different, really rich geometrical features. And what we really want to do is be able to rapidly prototype wings which can capture a lot of these different features. Now we're starting with an insect wing. You might protest and say, well, why are you just starting with an insect wing? And the reality is because we don't know any better. We're starting from basically very little information on these systems, so we figured it was best to mimic a system which does work. And so what we did was we take that three-dimensional data, create a three-dimensional CAD model, start to slice this And I'll show you how we recreate this in a minute, but one of the things that these next few slides are going to point out is that if we can make airfoils with these different morphological features, the first thing that we're starting to do is to say, well, what happens if I have basically a 2D versus a 3D wing, and what is the penalties that I pay for losing that third dimension? And then I'll come back to that in a minute. First question is, how do we make these things? We've decided upon a micromolding process which utilizes calibrated laser ablation of, in this case, silicon wafers, which you basically take your three-dimensional CAD models of the wings, you slice them, and use each of those slices to remove a layer of material from a silicon wafer to make micromolded channels. We can do this now. Mind you, of course, laser micromachining is a fundamentally aspect ratio limited process, so you're never going to get perfect sidewalls. But nonetheless, you can do a number of different profiles, and I won't get into the details of this. We had a paper in JMM not too long ago which describes the molding process. There's some engineering tricks here, like release layers and using compliant upper molds and rigid lower molds. But nonetheless, we can make these molds out of selective laser ablation. You can see the difference between corrugated and uncorrugated molds. We can make the wings using a molding process. And lo and behold, if you again go back and start poking on these wings and testing their static stiffness properties distributed over the surface of the wing, you get similar characteristics as you get in actual insects, and you do indeed, of course, see a dramatic difference between corrugated and non-corrugated wings. But that's not enough. We'd really like to test these things in a dynamic setting. And so what we've done is put a lot of emphasis into an overall system. It's in its second revision now. But the overall vision is the following. You have a system where you make certain wings. Maybe you put features on the wings. I'll get to that. You drive the wings with multiple degrees of freedom. One of the things I failed to mention is that we can now put feedback control on the internal state of the device, so that we can actually do feedback control over wing motions and get whatever wing motions we want for the most part. Drive the wings, mount it to a multi-axis force sensor, use multiple high-speed cameras to actually measure in an automatic fashion motions and deformations of the surface of the wing, and also illuminate with lasers and look at flow structures if we wanted to, using particle image velocimetry, and all trigger that and control that through an automated system. Here's one of the first generation results. Here's one of the wings that Dr. Hiroto Tanaka had made. Here it is, of course, at low frequencies. Now I'm only commanding flapping in this case, and of course there's no aerodynamic or inertial load, so it's not rotating with its passive dynamics. Here it is at high frequency. Okay, you all see that. Of course, you can't see what's going on, so we can start to do these side-by-side comparisons of, corrugated versus non-corrugated wings, and start to say, well, qualitatively, there's obviously something going on here. These are taken at 10,000 frames per second, and you can start to see the differences between the deformation patterns associated with corrugated versus uncorrugated wings, and it gets much worse, of course, if you start to go with higher aerodynamic loads. All right, but that's still not enough. That's still not quantitative enough for actually extracting anything more meaningful from these structures. What we really want to do is come up with some simplified model for what's going on here, and then use some of these experimental apparatus to actually look at any number of things. How is this being affected by Reynolds number? How is this being affected by wing aspect ratio? And I'm not going to get into all of those details. I'm going to only show you one result. But basically, we've set up a system. This is the first generation. I'll show you the second generation, where you take your wing structure and you mount it to a force transducer. I think that's on the next slide. Yes. It turns out that this is, I put this slide in here, which is just terribly boring subject, is we had to spend a lot of time actually manufacturing multi-axis force sensors. The reason being is that there's simply nothing off the shelf which will give you the features that you want. And what we want out of these systems is very high bandwidth and very good resolution. And those are paradoxical, of course. You can always make a force sensor, for example, have higher bandwidth by trading off bandwidth for sensitivity. It's almost like the electrical analog of having the gain bandwidth product of an operational amplifier. But nonetheless, you can't get away from that physical reality, and so we had to put a lot of effort into designing a structure which would work on these scales of 1 milligram resolution and 1 kilohertz bandwidth amounts to about 1% of body mass and about 10x the fundamental drive frequency for the vehicle scales of interest. Figure out a way to manufacture these things and also do everything we could possibly do for engineering tricks to minimize noise. So Electrical, thermal noise we minimize by making the structure out of an INVAR, which is an alloy that has the lowest CT of any alloy in existence, et cetera. Anyways, nonetheless, it's kind of boring, so I won't get into it, but it works. So that allows us to do real-time measurements of what's going on with the forces that we measure. We're also making torque sensors, which I'm not going to get into in this talk. Now let's take a step back and start to say, this is our standard wing, which is basically a wing we use to basically troubleshoot all of these different components of the system, where we can take the wing and use shadow masks to put a little chrome dots on the wing. I don't have slides on this, but we use some actual microscopy techniques in our high-speed videography to do backlighting so that we can get very high contrast, high resolution images of what's going on through the high-speed video. And then the question is, are there some of these techniques, and in this case, this is a technique that one of my students had done a couple years ago, which is to say there's these quasi-steady techniques that exist from work, for example, of Dickinson. People that are doing these dynamically scaled models can actually extract out force coefficients which hide all of those unsteady terms, which I showed you in one of the first slides, behind these time average force coefficients. You can't just do that. You actually have to look into other coefficients as well. But nonetheless, there's these quasi-steady models. Do they capture the characteristics that we want? Can we use some of these models to predict things like, well, not only what is the lift and drag that is acting on this particular wing integrated over the whole wing, but also can it predict the passive modes of the wing itself, given the fact that you have only one input into the system. So what we did was we take these wings, we take these multiple, this case 2, we're gearing up for 4 high-speed video camera images, known camera calibration, something called auto stereophotogrammetry. Non-auto stereophotogrammetry, for your information, is grad students clicking on dots. So taking multiple camera images and doing a bunch of vision tricks, but in the end getting out, you can see why we're getting out basically a 3D time history representation of all the tracked points. It drops out, and that's the reason we need to go to 3 or 4 cameras, is because even with 2 orthogonal views, you get some epipolar ambiguities when you try to do some of these vision tricks. But anyways, bottom line is, and you can ignore the stuff on the right, but on the left here is that the upper traces we're commanding wing flapping angle. We're actually measuring using the rigid body modes for example, from the previous video, that we can extract out both actually 3 angles of the wing motion: flapping, rotation, and deviation, and then also measure the forces that we're generating and predict the forces that we're generating based upon those motions in the quasi-steady model, and it matches up very well. The nice thing is there's no fitting here. It just works well enough. So the answer is, to my previous question, for this particular Reynolds number, and this is where you should protest and say, well, what about other Reynolds numbers or other features of the wing? And the answer is, well, that's ongoing. But for this particular Reynolds number, the quasi-steady version is pretty much the 80 or 90% answer. Okay. We also started some techniques where we can look into the flow structure that we see. So we have a system set up now where we can illuminate slices of the flow with a laser, and I won't bother telling you about it. I'll just show you. Hopefully this shows up, where we can take the same wing structure and seed the flow with some smoke particles and illuminate it with a light sheet, and then process that using basically commercial off-the-shelf PIV algorithms. And now, mind you, this is only true at mid-stroke because the laser sheet is not rotating with the wing. But nonetheless, you can still see some of these classical features which you would expect, like the buildup of a leading edge vortex and the shedding of a trailing edge vortex, et cetera. So this is the first PIV that's been done on flapping wing robotic insects, but that's cheating because nobody else really cares. Okay, so okay, next topic. I'm going to switch topics now. That work is ongoing. I'll be happy to talk to you about it, but basically that sets up the stage to do all of to basically set up the experimental infrastructure. There's things I'm not talking about. We're also developing environmentally controlled chambers where we can suck vacuum or actually fill with sulfur hexafluoride to do actually higher density measurements and all these other things, but I'm not going to get into that. I want to get into topics of control, and these are of interest to me. I was actually trained at Berkeley with some of these topics, and basically when I got to Berkeley, I was working with Ron Fearing, and this project called the Micromechanical Flying Insect Project had just started. Metin was working on it as well. And with my interest, I said, oh, this would be a great controls project to work on, and Ron basically said, well, you got to build them first. And so we went off on this tangent of these other topics. But nonetheless, now we're able to actually build the structures, and we can start to come back to think about some of these things. So the question is, we have these systems which we think that utilizing some of these passive dynamic modes, meaning these passive rotations associated with the wing pronation and supination, the fact that we're basically dumping all of our power into this primary power actuator, resonating the flapping mode, and allowing these other modes to appear passively, we think is a very efficient way to do this, basically to distribute power in the system. So what we don't want to do is start adding, if we want to create, for example, controlled body torques. If we want to create to create controlled body torques, maybe we want to create controlled wing asymmetric motions. We don't want to have these big other actuators drawing significant amounts of power and taking up this volume and mass, of course. So what we did was we looked into inspiration into diptera and thoracic mechanics, and that's basically, this is a very crude drawing of a fly thorax where you can start to say, how does this happening in flies? And I don't want to butcher this because I'm not a biologist, but there's basically a morphological separation of power muscles and control muscles. And what happens is there's these large sets of power muscles which are basically just resonating the thorax, the wing connected at the interface between the thorax and a deformable section and just basically flapping. And then you have what's, again, you can't really see it, but there's a number of these smaller control muscles, I think on the order of 20-something of these control muscles, which are inserting directly upon the base of the wing hinge and doing something. I don't think it's fully mapped out, but basically either injecting very small control torques onto the base of the wing, adding or removing energy into the system, to all for the purposes of creating controlled body torques through creating wing motion asymmetries. And so we went into basically some design of various different iterations of some thoracic mechanics, which include smaller control actuators, which are again smaller, lower power. They don't have to operate necessarily tonically with the wing beat frequency. We can do these things slower. We can do these things perhaps on scales of maybe 10 to 10 wing beats or so. Here's an example of one of the designs. What the point here is, if we take the previous kinematic chain that I showed a number of slides ago, and we say we want to create wing motion asymmetries. Well, how do we do that? Okay, well, there's a number of ways. I'm not going to proclaim that any of these are the optimal way to do it. They're just a couple of examples. One of the ways you can do it is thinking about where the mechanical grounds are in this transmission system and start to move those subtly. And if I move those mechanical grounds around, I can think about the transmission as two parallel gearboxes, and if I change the gear ratio on one, I'm going to have different input-output properties. And so we built a structure like this, and if you look carefully at these videos, what's happening here is that we have a control actuator which is on this side here, and all that it's doing is doing very slight changes, plus or minus 100 microns of difference in the position of this left ground link here, and so you can't see that. So if you overlay the maximums of the stroke amplitudes, you can see that there's actually a pronounced difference in the stroke amplitudes of the left wing, which is being actuated, versus the right wing, which is not. Okay, that's nice. We can also do things like incorporate different controlled degrees of freedom within the thoracic mechanics to get stroke plane deviation. I'm not going to get into that. So that's a set of mechanisms by which we can create controlled wing asymmetries. There's a whole another suite of topics to talk about that, but I want to move on to get to, okay, if you have the ability to control, let's say, modulate amplitude to modulate thrust, for example, or modulate wing asymmetries to modulate body torques, then what? And so there's a new, relatively new postdoc in my lab that's looking into adaptive control laws, which are basically using online in situ characterization methods by which we can take some of the similar mechanisms that I showed for aerodynamic characterization, where we have this wealth of data in terms of what are the forces that are being generated, what is the power input to the actuator, what is the displacement of what is basically the internal configuration of the system by measuring the displacement of the actuators, and we can take that, do an online characterization, do a dimensional reduction from actually taking the entire system down to something more tractable in terms of its dimensionality, looking at adaptive control laws, doing things like controlling wing motions and doing things like creating lookup tables for doing, in this case, thrust control, et cetera. And there's a couple of papers which we submitted on that. Okay, I'm breezing through that because for a reason. One of the reasons is that's fine, right? So you can, let's assume then that you can manufacture these systems and flap wings around and have some of these thoracic mechanics tricks to create asymmetric motions. We're assuming that those asymmetric motions create body torques, and that's fine. Then you do some characterization of that, and then you do some either classical or whatever control techniques you want to do on top of that. But here's an illustrative sort of figure is, at some point, you're going to have to do some computation in there, right? You're going to have to do some sensing of some perturbation, some attitude perturbation, for example, and then you're going to have to actuate that, or you're going to have to compute about that, think about that, come up with some control inputs into your actuators, and this is a big challenge. So this is put up here because these are typical components associated with larger scale computation with microprocessors that you might want to do this with. And so this is motivation for the following topic. Let's think about this for a minute. I'm going to come back to the concept of control, but let's think about this for a minute where we've already got an under-actuated system, and where we are commanding a flapping mode and we're allowing 2 passive degrees of freedom. Now, what happens if one of the wings is imbalanced, meaning if we have some fabrication issue which is causing some asymmetry between the drag torques in one wing versus the other? Well, what that means is that if I'm calling this roll and I have some asymmetries in the reaction torques at the base of the wing hinge, then I'm going to get a net roll torque. Okay. Now, similarly, think about if I'm driving around in a car without a differential mechanism, and I want to go for a turn, then my wheels are kinematically constrained to be the same, to operate at the same velocities, and so I'm going to have one of them slip because one of them needs to go at a longer distance in the same amount of time. Now, this was overcome many, 100 years ago with adding an additional passive mode into the system, which is an odd mode between the velocities of the 2 wheels called a differential. Everybody knows this. It's simple. It's well established. One of my students came up to me one day and said, well, why do we need to start thinking about what the wings are doing? We don't care what the wings are doing. These wings are strictly end effectors creating forces and torques which are acting about some point on the wing hinge, and all we really care about are these forces and torques. So why don't we generate systems like a differential? The differential, all it does is take an input torque and distribute it as necessary to the left and the right wheels such that distributes velocity to the left and the right wheels such that the reaction torques at the ground are equal. And so there's actually a number of different examples of this throughout different structures, wiper blades and Whipple trees, et cetera. We can do the exact same thing within our structures. So it's sort of counterintuitive where we start to think about including now an additional degree of freedom in the transmission system. And this is a case where we're concerned, like I said, with roll torques, although I'll get to other directions for this in a minute, where we do the sort of counterintuitive thing of taking an under-actuated system and making it more under-actuated by adding these passive degrees of freedom into the system. But if you do this well enough, what happens is that this passive degree of freedom, just like a car differential, will act to balance, to distribute torques from the base of the reaction torques from the base of one wing hinge to the base of the other such that they're equal. What that means is we've done experiments where we created these systems and put this additional degree of freedom in. If the wings are nominally equal and you have this single actuator input, then the wing motions are going to be nominally the same because the torques are going to be the same, and so the velocities are going to be the same. What happens is if we start to lop off sections of the wing, then you're going to get dramatic differences in the aerodynamic and inertial loads that you see, and in particular the reaction torques that you see as a function of those loads. And what's going to happen is if I lop off let's say my right wing, then I'm going to have less loads there, and so there's going to be a torque imbalance unless the system flaps that wing faster, and that's exactly what happens. And so this is a concept which he calls passive aeromechanical regulation of imbalanced torques, or parity. I don't know where the Y comes from, but it actually works remarkably well in both simulation and multiple different levels of experiments, which I'm not showing here. And in fact, he won best student paper at RSS for this concept. And the whole concept, which is what we're trying to frame now, is the classical thing that you think about in these systems is, well, I've got some undesired input into my system, a torque. I've got something which is sensing that. I do some computation on it. I then have some actuator input to correct it, and there's my feedback loop. Well, no, let's do this all mechanically in a concept that we're thinking about with mechanical intelligence. This is a diagram which I'm not going to get into because we haven't built it yet, but basically we can extend this concept to all body degrees of freedom. And the nice thing about this is what this acts is basically an automatic rejection of high frequency perturbations and allows you to think about control on a very slow time scale. So it alleviates, it's not going to solve all computation tricks, but of course it's going to alleviate the needs of computation for these systems, which are going to be extremely computation limited. Okay, the last major topic I'm going to talk about are power electronics. One of the things I didn't mention, okay, well here's our assumptions for what we might have. I mentioned that we have this collaboration with Sriram Ramanathan, who actually recently had a paper out which demonstrated the world's highest energy density on-chip microfuel cells. I don't know the numbers, but and also the lowest temperature, which is important from my very limited understanding of the chemistry of those systems. But the low risk is of course lithium polymer batteries. We've been doing a very silly thing, which it's very silly. Turns out that you can, all of these different batteries that we see, lithium polymers, for example, you can watch the trend of these batteries as they scale down, and in terms of their capacity as a function of scale, and you know, they follow a pretty good trend. They don't get down as small as we would need. If they did, they would seem to work okay, and that was actually going back to our previous discussion on our assumptions for flight time are based upon some of these numbers, but they don't exist in the form factors that we want. And so actually what you can do is you can go in an inert atmosphere and cut these things apart and tape them up back together in a smaller form factor, which is very silly. Nonetheless, that's not important. Actuation I already told you about. One of the difficulties associated with these actuators is that they require relatively high voltages. And so how do we take these battery voltages from, or these voltages from, you know, 3-ish volts up to 200 to 300 volts, and do this in a 10 milligram scale package, and do this with very high efficiency. And furthermore, one of the subtleties about this is that we have these systems, for example, like a bimorph, where you're putting charge on one of the half plates, or one of the plates for one half of the cycle. It has relatively poor electromechanical coupling, and so there's going to be some residual charge there. So you don't want to just throw that away. Instead, what you do is for one period of harmonic oscillation, you take charge from one half period and put it on the other plate for the next half period. And of course, that actually increases. It's almost necessary to do that. Increases your efficiency of the whole system from about 5% to like 20 to 30%. And there's multiple different drive layer topologies which we can do. For example, single stage circuits which both boost and amplify drive signals into the actuator directly, or dual stage circuits which do a separate boost converter and then distribute high voltage to the plates of the actuator in a separate stage. I won't get into too many of these details because I don't know if you guys would be terribly interested. The ones that we're implementing now are these tapped inductor boost converter circuits, which amplify based upon turns ratios and switching duty cycles, and they can get us from battery voltage to a couple hundred volts in very high efficiencies. And we've actually just taped out a circuit which does exactly this, which is now think about how to do that charge recovery by intelligently taking little packets of charge and putting them on both of the plates as required by an external controller. One of the issues, though, is how do we actually build these things? And we do this using a lot of, well, the least amount of discrete components as possible for the first iterations. One of the unfortunate things about all of these different circuit topologies that we've considered, the tapped inductor boost auto transformer circuits, things like piezoelectric transformers, or things like charge pump ladder stages, all going to require some external components at this point. And so in this case, it's going to be magnetic components. So nothing off the shelf existed, of course. So what we did was we took these ferrite materials and laser micromachine E-cores and built a winding system to make some of the highest energy density magnetic components for these scales. But again, nobody really cares other than us. We also have some bare die high voltage transistors, and we've recently taped out, I'm not including any information on it, but we've recently taped out the control circuit to do this, and it actually entirely works. And so I actually had one of the points here is at the point of the takeoff video that I showed you, we had basically an external controller, which was, piezo amps and signal processing, et cetera, which is this big 200 kilogram rack. And I said to my student, Mike Carpelson, I said, well, you get 200 kilograms down to 10 milligrams and you can graduate. And he's actually graduating soon. So, okay, so let's see. The next steps, and I guess I have a few minutes to talk about a couple of the other, I'm just going to throw plugs at you for a couple of our other programs, which you may or may not be interested in. First is, what is the current and future work? Well, I don't need to really go into this, but different thoracic mechanics designs, control experiments. We're just in the process of setting up different control experiments, in particular altitude control and attitude control experiments. Aerodynamics testing. This is the subject of another PhD student, Peter Whitney, who's doing now ramping up to do some of those same aerodynamic studies, but across a variety of range of different wing morphological parameters. Actually doing integration of some of the power electronics and power sources onto the structure to do some of the same very simple lift to weight measurements. Actuator optimizations, there's a little bit left to squeeze out of the actuators. New fabrication techniques, studies on multiple wings, et cetera. RoboBees. So we recently got together a team of people, mostly at Harvard, but that I'm the PIing with, like I said, mostly Harvard people. And we went and pitched this concept of a colony of autonomous robotic bees to the NSF and their Expeditions in Computing, which is the largest grant that the NSF had, the largest non-center grant that the NSF has. And they liked it, so they said go ahead. And what we're doing in this is we've separated the project, the creation of autonomous robotic bees. Okay, so you know that. We've separated it actually into three different components: body, all things associated with the flight apparatus. This, of course, is leveraging some of the work that we have previously done and are currently doing in my lab, as well as some collaborations with some biologists. Brain, which is all things associated with sensors. We're collaborating with some vision experts, as well as some a guy named Jeff Barrows, who has a small company making insect-inspired vision sensors. Colony, which is thinking about how to have coordination algorithms which are greater than the, cause these things in aggregate to be a greater performance than the sum of the parts. Things like distributed operating systems and coordination algorithms. We also have a fair bit of outreach activity in this. Here are the people. Anyways, not that you really care, but the goal is a coordinated colony of robotic bees. And I think that's it. So I'll plug a couple of things here. So I'm not quite done. This is my group and our sponsors. So thanks so much to them. Of course, they're the ones who are much smarter than me, and they do all of the hard work. Thanks to Mr. Obama, and I guess one of the bad things about being tall is that I'm always in the back row. Okay, so there's a couple other programs that I wanted to plug. One is a program which is, well, a collection of topics on soft robotics, where we're looking into a number of new material combinations, actuator technologies. On the left is actually a new concept that was inspired by catch connective tissue of sea sponges, where they can actually change their bulk stiffness properties by orders of magnitude by selectively cross-linking fibers in their internal structure. And we've done similar things, conceptually similar things, with confined magnetic domains at relatively low magnetic fields. We've also made squishy robots, which, and this is just a worm-like robot operating on peristaltic motion. You can see this is sort of ominous. This is the work of Sang-Bae Kim when he was in my lab. Yeah. By the way, this is not good. TSA does not like structures like this. Okay, we've also been having some work in, now this is another soft robotics project where we're trying to embed functionality, a wide spectrum of functionality: sensors, actuators, electrical functionality, resistors, capacitors, inductors, gated components, stiffness change components, all within entirely soft structures. So no tricks here. No, you can get softness out of different geometric tricks or materials. We use entirely soft or liquid phase materials. And this is just an example of a stretchable, of a hyperelastic plastic keypad that they made with the way that this is made here is basically by multiple layers of microfluidic channels filled with a room temperature liquid metal, which is the eutectic alloy of gallium and indium. So it enables things like human-computer interfaces, and there's actually a project sponsored by the NSF which is looking into entirely wearable assistive orthotic devices to correct for people with neuromuscular disorders, or to assist people with neuromuscular disorders. Another one is programmable matter, where we had the concept with a team at MIT, Berkeley, and Penn, where we were creating self-folding sheets of robotic origami to make basically reconfigurable systems. One of the things that I guess was the motivation here, we were mostly on the mechanics and actuation side, but one of the motivations of these sheets was not only were we working with Eric Demain, who's a computational origami expert, but also because you alleviate some of the considerations of making and breaking connections by having these. And this was a couple of simple shapes that we made. You can kind of get the idea. This is real time, so very slow. Anyways, this kind of grew out of some of the layered laser machine techniques that we use for these robots as well. And I think this is the last slide. We actually do some work in ambulatory structures where we make hexapod-like robots, myriapod, centipede-inspired like robots, where we are using these things again not just to make cool robots, but to study things like, well, what is the optimum number of legs? How can we think about, can we start to test the Bob Full-like things of how compliant the leg needs to be as a function of body mass and operating frequencies and all these other things, as well as to push for things like this, batch fabrication, batch mesoscale fabrication techniques. Yeah, the most interesting part of the video is the last half second, but the nice thing about using some of these techniques is that they have relatively high bandwidth. So I think that's it. Yes, that's it. Is this for me?
We have time for some good questions.
Yes.
So some of your charts, comparison of biological organisms, had Lepidoptera and some of them did. What changes if you get to a really big butterfly with really slow climbing?
That's an excellent question. So there's a couple of ways to answer that from our particular technologies. Like I said, for these piezo actuators, they're not going to do too well because of the low operating frequencies are going to cause their power density to decrease substantially. But the other answer that I'll give is actually we have a program which has recently started to actually look at hybrid flapping and gliding flights and strategies which would perhaps take advantage of systems optimized for both and not just one or the other. And so I don't know if I have a good answer for that yet, but hopefully in a couple of years we can answer that. Yeah, it certainly is true. I would argue that lepidopterans and others, Odonata in some cases, you actually use soaring mechanisms in their flight, right? Which is not terribly effective at low Reynolds numbers, where you're going to get lift to drags, not in the hundreds that you get from a sailplane, but on the order of 1 or 2, right? So it's it'd be interesting to see what needs to happen in terms of not just shape optimization, but surface textures, boundary layer trips, anything which is going to promote adhesion of these of these vortex structures or whatever. So this is what we're studying. Don't know. Sorry. Yeah.
Yeah, I liked your definition of mechanical intelligence here. You're trying to get the computer out or some processing element out. It seems like a great idea, especially when you're trying to do some specific kind of control scheme without having to worry about all kinds of processing in there. But have you thought about how you do some sort of changes in phases? Like you need to do something, then you need to do something qualitatively different, then you need to do something, so take off or flight or approach or approach or landing. These might require. Have you thought about a way to sort of encode that
Yes.
level of abstraction mechanically?
I think I can answer that. And what if you take this system for? Let me see. Is this the best diagram? If you take this system, for example, this is measuring, what happens is that there's torques that are generated, reaction torques that are generated, let's call it roll, which is along sort of these axes at the base of each wing hinge, okay? And if they're equal, then nothing happens. It looks like the previous transmission. If they're not equal, what happens is that there's greater force on one side than the other, and by the geometry of this transmission mechanism, it'll act to increase velocity until those forces are equalized. What you can do is now, that's in a perfect world, that's just keeping you sort of steady. That's rejecting any perturbations of torques and these various axes. But you don't want to just sit there, right? Like you're saying, you want to move forward. You want to do something else. So what you can do is, we haven't done this yet, but you can imagine taking this and moving it just from side to side. Now you're balancing your reaction torques about a different equilibrium position, which is not balanced. But it nonetheless still takes care of your higher order perturbations, high frequency perturbations. And so it has those nice features, but now you can sort of change that basically the fulcrum of the seesaw, you change it on a slower time constant. So is that along the lines of what you're thinking of?
Yeah, that's one.
Yeah.
I mean, there's
I'm sure there's many, I'm sure. Yeah.
Different things, right?
Yeah.
From takeoff to descent, for example.
Sure.
They're probably coupled a lot more with the perception.
Yes, true, yeah. So that, I mean, I guess that's an overly simplified way that we've been thinking about, is basically taking these balanced equilibrium systems and then changing where they're balancing around. Slava.
So you said that you concentrated a lot of the effort on the design of the wing. You looked into some information about three-dimensionality with corrugation and so forth. Have you found any sort of significant increases in lift from the corrugation, from the layer of the shading policy?
Yeah, I didn't include that because it's too preliminary, but yeah, our initial indications indicate that if you, the lift that you can generate for the same mass and input conditions, wing mass, wing inertia, input conditions, but with corrugation without, that we have indication that you can, the corrugated structures are outperforming.
The percentages would be like 30%?
Yeah, I don't remember off the top of my head, yeah. I don't think we haven't done enough of a study for me to really say concretely, but initial indications are that, yeah. But that could be biased. I mean, because if you look at we need to compare apples to apples here, and what really is happening is that the non-corrugated, the flat wings are deforming so much that it's hard to define the axis of rotation, and you know how these things are actually deforming are obviously affecting their thrust. So we need to come up, and we have some thoughts on this, of a more apples to apples comparison where perhaps you don't allow passive rotation. You make sure that the rotation is actually arising out of deformation of the wing itself, for example, and that might help with that. But that's how we.
So I have a two-part question. So the first is with the, I think we called you robotic, the thing with the sensor, the tactile sensor.
Yeah.
What kind of support electronics, support power, support computation does it need? And really the question I'm asking is what will it take to get it on my Snake robot?
Actually, when we were talking earlier, this is one of the things I was thinking about. So, sorry, let me get to it.
Great minds think alike.
Okay, so I don't know why I needed to bring this up, but not much. These things are very easy to make. They're standard microfluidics soft lithography techniques to make these channels. There's some tricks in filling the channels with the liquid metal, but that's just an engineering trick. You were asking about what is the back-end signal conditioning, and it's very, very little. So what happens here is that the way that these things work there's pressure, strain, and curvature modes, and you can decipher between the three just by geometry, just by two-dimensional and 2.5-dimensional geometry. And what happens in these cases is quite simple. I push down. There's rows and columns, and as I push down on a part of this, then it's changing the cross-sectional geometry of that area underneath where I'm pressing, and it's a liquid metal. You're changing the cross-section of the channel that the metal is filled in, so you're changing the resistance, and so you just measure it as a resistance change.
And how robust is this? How much you beat the crap out of it?
We've got I don't say this. I'm sorry. With PDMS versions, you can get up to 300% strain. We actually wrote a paper and stressed from the failure. With other versions, like EcoFlex versions, are slightly more difficult to make, but 1,000% strain.
Okay. So then my follow-up question to that is, so the devices you presented are impressive. I'm not trying to be an armchair micro aerial vehicle guy. I think let's just push you a little bit,
Yep.
maybe 5, 10 years from now. So I was wondering about the issue about onboard power for all of your devices. I realize there's other things you have to think about first. And it would seem to me that on the scales you're talking about, there are other power issues that, above and beyond power density. Like, for example, is heat an issue?
I see.
So I'm curious, what are those issues? What are those issues you have? And the follow-up to that would be, if you had the added weight and all these other added issues with onboard power, how would that change your designs? Would your wing flap be longer or stroke faster or something like that?
So I think your first question is asking about integration issues when you start to put all these things together. If you have a battery, if we're operating over a minute, then, or let's say 6 minutes, then we're operating a battery at 10C discharge rates, which are going to be, decreased capacity. So that's the first thing is, we've thought about this a little bit by having some relatively simple models for derating battery capacity as a function of discharge rate, although there's nothing analytical yet for that. Heat, yes, you're going to be heating things up through internal resistance of the battery. Maybe even more importantly is our collaborators are working on getting microfuel cells to operate at lower temperatures, but those lower temperatures are still hundreds of degrees C. And so how does that affect everything from material properties to air density? I don't know yet. That's an excellent question.
Are there other issues beyond heat that look at that scale?
Indigestion and flocks of birds that say these things and mistake them for the real thing.
Yeah, that could happen.
Yeah, I think the big thing I think you touched upon, which is how are all of these components going to, on paper each one of these components works well, and in individual experiments they might work well, but when you put them all together and start sucking enormous amounts of energy out of the batteries in a short time scale, are they going to explode? Are they going to, how are the wire bonds between individual components going to stand up to oscillations at these? So yeah, these are engineering tricks and challenges which I'm sure we're going to encounter. It's hard for me to predict, though.
Okay, I don't want to push you anymore. Thank you for your questions, for your answers. Any more questions? Time for one more question. All right, well, let's thank our speaker again.
Thank you.